Welcome to our new video series. We're testing out newer approaches to explain AI, and we need your feedback. Is it too easy? Too complex? Let us know in the comments. We love hearing your ideas for future videos as well. Please share, like, and subscribe if you find this useful. Today we are diving into one of the most exciting and rapidly evolving areas in artificial intelligence: multi-agent systems. We call this presentation the Agentic Heist, because building complex AI solutions today is less about finding a single genius operator and more about assembling a specialized, coordinated team, a crew to tackle a high-stakes problem. If you are building complex AI applications, moving beyond a single large language model acting alone is the fundamental architectural shift you need to make. We are going to provide you with a blueprint for designing these multi-agent AI systems, focusing on how to decompose massive tasks into manageable roles, how to coordinate those specialized agents, and ultimately, how to achieve complex objectives that would be impossible for any solitary agent. Think of this as the definitive guide to moving from a single operator to a specialized crew. Before we can build a crew, we must understand why the lone genius approach fails. We call the limits of single-agent systems the mark, why one virtuoso can't crack the vault. Single-agent AI systems, regardless of how powerful the underlying model is, face strict architectural limits when presented with complex, multi-step workflows. Much like a lone operator trying to manage a sophisticated, multi-stage heist, they break down under pressure. The fundamental problem isn't a lack of intelligence, it is cognitive overload. We see this breakdown manifesting in three primary ways. First, context window saturation. As the task context grows, the agent's attention fractures. Critical, early details get buried under later information, leading directly to hallucinations and incorrect decisions. This is the operator trying to memorize blueprints, guard schedules, and passcodes all at once. Second, tool selection degradation. As the number of available tools increases, the decision fatigue degrades performance. Microsoft's analysis of real production systems provides stark evidence here. Tool selection accuracy drops severely, falling from 94% accuracy when the agent has only 3 to 5 tools available, down to a mere 73% accuracy when it is forced to manage 15 or more tools. Finally, the maintenance nightmare. Monolithic agent prompts, where all logic is contained in one massive instruction set, are extremely brittle. Adding a new capability risks breaking existing logic due to tight coupling, making debugging a misery. As one developer noted, they spent more time debugging our mega agent than we would have building a modular system from scratch. The solution to the virtuoso problem isn't simply a smarter agent, it requires a fundamentally smarter architecture. We adopt what we call the heist mentality, achieving decomposition through specialization. By creating a team of specialists, where each agent masters only a narrow domain, we directly address the failure modes of the single-agent system. This approach is built on 3 core architectural principles. The first is bounded complexity. Each agent manages a smaller, relevant context, fewer tools, and consequently, narrower responsibilities. The benefit here is clear. It keeps context relevant, prevents saturation, and makes tool selection highly tractable. The second principle is modularity. Agents can be developed, tested, and deployed independently. This provides the major benefit that new capabilities can be added or old ones can be swapped out without ever rewriting the core logic of the entire system, eliminating the maintenance nightmare. The third principle is resilience. Agent failure is localized. If one specialist is compromised or fails a task, the rest of the mission can adapt and recover. The benefit is that the overall system degrades gracefully rather than failing catastrophically. However, we must recognize that these benefits come with a cost: coordination overhead. The art of agent architecture is choosing the right playbook or topology for the job to minimize this cost. To run a successful operation, we need a specialized crew. We begin by assembling the crew, focusing first on the brain trust of the operation, the strategic agents. We define 2 primary roles here. First, we have the supervisor, often nicknamed the mastermind. The supervisor's function is to manage the overall workflow, delegate tasks effectively, and ensure the entire team remains aligned with the high-level mission objective. This agent serves as the central orchestration authority. Their core responsibilities include task assignment and delegation, continuous progress monitoring, conflict resolution between agents who may disagree on the next step, and robust failure handling and recovery protocols. They keep the mission moving forward. The second critical role is the planner, or the architect. The planner receives those high-level goals from the user or the supervisor and is responsible for decomposing them into a structured, step-by-step execution plan. This agent reasons specifically about task structure, analyzes dependencies between steps, and determines the correct sequencing. The planner's core responsibilities involve goal interpretation and clarification, detailed task decomposition and dependency analysis, accurate resource estimation for time and tools, and crucially, contingency planning to prepare for expected roadblocks. Together, these two strategic roles translate vague instructions into a concrete, executable roadmap. Moving beyond the strategic layer, we now assemble the specialists on the ground, the agents who execute the core work of the mission. We define three essential operational roles here. First, we have the researcher, or the intel specialist. This agent specializes entirely in information gathering. Their function is to formulate precise queries, retrieve data from multiple diverse sources, and then synthesize those findings into coherent, actionable intelligence for the rest of the team. Their core capabilities include multi-source retrieval, source credibility evaluation to prevent reliance on faulty information, advanced synthesis, and summarization skills. Next is the executor, often called the operator. This is the hands-on agent that takes the planner's instructions and acts upon them. Their function involves calling APIs, executing code in a sandboxed environment, and interacting directly with external systems. The executor's core responsibilities focus on reliable tool and function calling, sophisticated error handling with retry logic, and precise result parsing to deliver structured output back to the team. Finally, we introduce the critic, or the failsafe. This agent is the guardian of quality. Its function is to evaluate outputs from all other agents against predefined quality criteria. Critically, the critic does not generate content. It only assesses and provides detailed feedback, often used in a reflection loop. Its core evaluation dimensions cover accuracy, completeness, coherence, compliance with instructions, and safety protocols. A crew, no matter how skilled its individual members are, is only as good as its plan. The way agents coordinate, their topology, is what ultimately determines success. Choosing the right playbook depends heavily on the specific nature of your task, and here we present our decision framework for 5 core ways to run the job. We analyze this framework based on 4 key dimensions. The first is workflow type. If the steps are deterministic or known, you should use the sequential or coordinator patterns. If the path is dynamic or emergent, you must choose hierarchical, blackboard, or swarm. The second dimension is task complexity. Simple tasks requiring fewer than 5 steps should use sequential. Moderate tasks, 5 to 15 steps, require a coordinator. Complex or recursive tasks involving more than 15 steps demand the powerful recursive decomposition capabilities of a hierarchical structure. Third is the primary goal. If your task is efficiency critical, stick to sequential or coordinator to minimize overhead. If the goal is creativity critical, requiring diverse perspectives and iterative refinement, you should use Blackboard or Swarm. Finally, consider the resource budget, which covers latency and tokens. Low or constrained budgets necessitate the use of sequential or coordinator. If your budget is high or flexible, you can afford the powerful collaboration capabilities of Blackboard or Swarm. For rough planning, Google's research offers guidelines on token usage. Sequential costs about 5,000 tokens, coordinator around 8,000, hierarchical 12,000, Blackboard 15,000, and Swarm is the most resource-intensive at 20,000 tokens per major task. Let's dive into the first 2 of our 5 blueprints, the linear and centralized plays. These are the most resource-efficient and deterministic patterns. The first is the sequential pattern, which we nickname the assembly line. In this pattern, Agent 1 passes its output to Agent 2, which in turn passes it to Agent 3, and so on. It is a linear, predetermined sequence of operations. This pattern is best for workflows with clear, linear dependencies, such as document generation or a structured data processing pipeline. A key insight from industry research shows that simple forward-only pipelines succeed about 78% of the time. This is decent, but to truly optimize performance without adding radical complexity, you can integrate a simple backward feedback loop. Adding this mechanism, where the subsequent agent provides feedback to the previous, boosts success dramatically to 91%, though it comes at a slight cost of complexity. The second pattern is the coordinator pattern, known as the project manager. Here, a central supervisor agent analyzes the initial request, decomposes it into subtasks, and then dispatches those subtasks concurrently or sequentially to various specialist agents. It maintains centralized control. This pattern is best for tasks where requirements vary significantly across different requests, requiring runtime adaptability in task decomposition and dispatch. The critical trade-off here is latency versus error reduction. Google's benchmarking shows that this coordination pattern typically adds about 300 to 500 milliseconds of latency per request. But this overhead is highly worthwhile as it reduces error rates by a substantial 24% on complex multi-step tasks. Now we examine the three most powerful coordination blueprints, the advanced and emergent plays, which are designed for ill-defined and complex problems. First, we have the hierarchical pattern, or the corporate structure. In this design, a root agent delegates tasks to multiple manager agents, who in turn delegate and supervise specialized worker agents. This creates a multi-level command chain. This pattern is best for ambiguous, open-ended problems that resist predefined workflows and specifically require recursive decomposition, such as creating a highly complex piece of software. Next is the blackboard pattern, the war room. This is fundamentally different because agents do not speak directly to each other. Instead, they read from and write to a shared memory space, which is the blackboard. A control unit is responsible for monitoring the blackboard and selecting which agent is best positioned to contribute next. This is ideal for ill-defined problems where the final solution path emerges iteratively from collective intelligence, like complex scientific modeling. A CAS study showed this pattern reduced token use by 35% while improving overall success rates by 12%. Finally, we have the swarm pattern, the emergent collective. In a swarm, centralized control is entirely removed. Agents operate as autonomous peers, and the workflow emerges spontaneously from local agent to agent decisions and interactions. This pattern is best for creative tasks requiring diverse perspectives, simultaneous evaluation, and active debate, such as brainstorming or critique sessions. Human evaluators rated swarm outputs 34% higher on novelty and 28% higher on overall comprehensiveness compared to single-agent outputs. The ability to execute a complex multi-agent job successfully depends heavily on robust communication protocols and a solid contingency plan. In terms of communication, we look at task handoffs. These can utilize a push model, which is coordinator-driven, where the mastermind explicitly routes tasks to agents, offering deterministic control. Or they can use a pull model, which is agent-driven, where specialists claim tasks from a shared queue, which enables parallelism. For information exchange, structured protocols are key. We recommend standardizing on protocols like request-response, publish-subscribe, or Blackboard events depending on your chosen topology. The best practice, regardless of the protocol, is to use structured JSON for inter-agent communication, not free-form text. This standardization drastically improves reliability and parsability. Just as important is failure recovery, the contingency plan. Agent systems are distributed and they will fail. Robust systems anticipate this and recover gracefully using 5 core strategies. First, retry with backoff for transient network or API failures. Second, failover, routing the task to a backup agent with similar capabilities. Third, degrade gracefully, routing the task to a generalist agent for a less optimal but still functional outcome. Fourth, quarantine, immediately isolating the failing agent to prevent error propagation throughout the system. And fifth, human escalation. For high-stakes tasks, critical failure triggers an immediate human review. Moving into advanced architectural moves, we introduce the self-correction loop, built on the reflection pattern. The best operators in any field check their own work, and multi-agent systems can bake this concept in natively. Reflection allows an agent system to rigorously evaluate its own output and iteratively improve it, ensuring higher quality and accuracy than a single pass generation. The process flows in a continuous cycle. First, the generator agent produces the initial output, such as code or text. Second, the output is passed to the critique stage, where a dedicated critic agent evaluates it against predefined quality criteria, checking for factors like accuracy, style, and functionality. Third, the critic provides specific, actionable feedback to the generator. Finally, the generator revises its output in the refine stage based on that feedback, and the loop repeats until the criteria are met. This process has a proven impact. Research shows reflection improves accuracy by 15 to 30% on complex tasks. It essentially bakes a continuous quality assurance process directly into the generation workflow. A vital implementation tip is to use different large language models for the generator and the critic. For the generator, use a creative, high-temperature model. For the critic, use a rigorous, low-temperature model. This architectural separation helps prevent the system from reinforcing shared biases or blind spots. Our second advanced move is the devil's advocate, which utilizes the debate pattern. Groupthink is the enemy of any successful operation, and this pattern is specifically designed to prevent confirmation bias by pitting agents with opposing viewpoints against each other. The goal is to explore the problem space thoroughly before a final decision is made. The architecture typically consists of 3 agents. A proponent agent argues vigorously in favor of a proposition, focusing on its potential benefits and opportunities. An opponent agent argues against the proposition, focusing on execution risks, hidden costs, and potential pitfalls. Overseeing this exchange is a neutral agent or moderator, which evaluates the strength of both arguments, surfaces the hidden assumptions, and ultimately makes a final recommendation or declares a winner based on the defined metrics. A perfect use case for this is strategic decision-making, such as a company considering market expansion. One agent can argue for the market opportunity, while the other argues against the execution risk. The key benefit here is that studies show debate-based systems produce far more robust decisions, rated 28% higher on comprehensiveness by human evaluators. The critical implementation nuance to remember is to use fixed turn limits, such as 3 rounds of debate, to prevent endless loops and ensure that a decision is reached in a timely manner. No AI system should operate completely autonomously, especially when dealing with high-stakes tasks. The concept of the inside man, keeping humans in control, revolves around human in the loop, or HITL, which is not just a safety net, but a core design pattern for managing risk, handling unforeseen edge cases, and enabling continuous system improvement. We define 5 essential HITL mechanisms. First, approval gates. The agent proposes a critical, irreversible action, such as deploying code or sending a high-value email, and a human must approve or reject the action before execution proceeds. Second, confidence-based routing. The agent evaluates its own confidence level in a result. If the confidence falls below a set threshold, the task is automatically escalated to a human expert for review. Third, escalation paths. If the agent encounters a task that is out of scope, or if a failure occurs that the system cannot recover from gracefully, the task is routed immediately to a human operator with all of the necessary context attached. Fourth, audit first. All agent actions and decisions are meticulously logged for human review post hoc, which is absolutely crucial for compliance, monitoring, and debugging. Fifth, the feedback loop. Human corrections, decisions, and outcomes are fed back into the system as training data to improve the AI's future performance and decision-making capabilities. The key technical challenge architects face when implementing HITL is that these workflows must be designed to be asynchronous, persisting the system's state while waiting for human input, which may take hours or even days. These multi-agent architectures are not just theoretical concepts, they are already delivering immense value across various industries. We highlight the payoff, 4 successful heists, demonstrating the power of specialization. First, R&D acceleration used by companies like Stemtology. The crew involves agents for literature search, data extraction, and hypothesis generation. They use a sequential playbook with feedback loops. The payoff is substantial, reducing literature review time from weeks down to hours, leading to a 3x acceleration in R&D cycles. Second, sales pipeline automation. The crew includes prospecting, qualification, and outreach agents, leveraging the coordinator playbook with parallel execution. McKinsey reports a tangible payoff, a 10% revenue uplift, and a 15 to 20% increase in the time sales reps spend on customer-facing activities. Third, financial intelligence, often found in trading agents. The crew is highly specialized, including analyst agents, bull or bear researchers, and a dedicated risk manager. Their playbook is blackboard architecture combined with the powerful debate pattern. The payoff here is reduced confirmation bias, leading directly to improved portfolio values and significantly better risk-adjusted returns. Finally, SecOps alert triage. The crew includes ingestion, enrichment, investigation, and remediation agents. They rely on the robust hierarchical playbook with integrated human escalation paths. The payoff is a reduction in mean time to remediate, or MTTR, by over 60%, while simultaneously decreasing analyst burnout by automating the tedious initial steps of investigation. While multi-agent systems unlock unprecedented complexity, they introduce new architectural challenges. A successful deployment hinges on anticipating and mitigating these trade-offs from day one. The first challenge is coordination overhead. Every agent interaction adds latency and token costs. A 5-agent system can easily make 20+ large language model calls per task. The mitigation strategy involves caching common subtasks, batching operations where possible, and using smaller, cheaper models like GPT 3.5 Turbo for simpler agents dedicated to tasks like classification. The second challenge is state management complexity. Tracking the state of a distributed system where failures can happen anywhere is inherently difficult. The mitigation involves using a centralized state store, designing operations to be idempotent so they can be safely repeated, and implementing checkpointing for robust recovery. The third challenge is debugging and observability. Pinpointing failure in a multi-agent system often raises the question, who is to blame? We mitigate this by implementing structured logging, using trace IDs to track requests across agents, and visualizing interaction flows. Frameworks like AutoGen and LangGraph offer essential open telemetry integration for this purpose. Finally, we discuss when not to run this play. You should absolutely avoid multi-agent systems for simple, single-step tasks, for applications with extremely low latency needs, or when operating on a severely limited budget. The ultimate rule is to start simple. Add agents only when single-agent limitations become measurable empirical problems that inhibit your mission success. We conclude with the architect's takeaway: orchestrating intelligence. The core message is clear. Multi-agent systems represent a fundamental architectural shift in AI. We are moving away from the pursuit of building a single, impossibly complex, virtuoso agent, toward creating teams of specialized agents that collaborate, enabling us to achieve complex goals that no single agent could ever accomplish alone. This entire process relies on 3 key principles that every architect must remember. First, the blueprint matters. You must choose coordination topologies or playbooks that precisely match the structure and requirements of your specific problem, be it sequential, coordinator, or swarm. Second, the crew is key. Success depends on decomposing cognitive functions into specialized, tightly defined roles, such as the planner, the executor, and the critic, to amplify overall team capabilities. Third, the protocols are the glue. Explicit collaboration and robust failure handling mechanisms are what determine success or chaos in a distributed system. Your job as an architect is not to play every instrument in the orchestra. Your job is to design the blueprint, assemble the crew, establish the comms protocols, and then allow your agent team to execute the complex job that no single operator could ever hope to accomplish alone.